Hello learners, welcome to this course on Fundamentals and Programming of 8085 Microprocessor. In this tutorial, I will be discussing about the features and pin-out details of 8085 Microprocessor. So first let us start with the features of 8085 Microprocessor. 8085 Microprocessor is a 8-bit microprocessor, which means it can handle 8-bit arithmetic and logical operations. So the arithmetic operations are addition, subtraction, logical operations are AND, OR, XOR, NOT, etc. So ALU gets data from the memories and it can perform 8-bit arithmetic and logical operations. So that is why 8085 is called as an 8-bit microprocessor. So it comes as a 40-pin ceramic dual inline package. So the IC is made up of a ceramic material. On each side it has 20 pins. It is manufactured with NMOS technology and it requires a power supply voltage of 5 volt. A crystal of about 6.144 MHz can be connected to the 8085 microprocessor, and this frequency is internally divided by 2, which means it becomes 3.072 MHz, and this is the operation frequency of your 8085 microprocessor. So each T state is made up of 1 by 3.072 MHz time period. And an 8085 microprocessor, it supports von Neumann architecture, meaning it can be interfaced with the memory which can hold program as well as data, and also the stack content can be stored onto the same memory. So we can interface a memory which can hold the programs, data as well as the stack content. So program memory or the program space in the memory, it will be used for storing the instructions. The data space in the memory will be used for storing the data, and the stack memory or the stack space in the memory is used for storing the context information. So whenever there is a subroutine call or whenever there is an interrupt to be serviced, in that case the interrupt service routine will be executed. So during those situations, so before moving on to the subroutine or to the interrupt service routine, the return address and also the associated registers for the main program needs to be saved in some memory location. So for that we can make use of this stack memory. Same way, after coming out from a subroutine or from an interrupt service routine, the context need to be retrieved so that the main program can resume seamlessly. So those information can be stored in the stack memory. So we have the total memory size which can be connected to your 8085 microprocessor is of 64 kilobyte. So it has a 16-bit address bus. So 16-bit address bus in the sense it can access, the CPU can access about 2 power 16 memory locations. So 65536 memory locations, and in each location 1 byte of data can be stored. So the total capacity of the memory which it can be interfaced with your 8085 microprocessor is 65536 bytes of memory can be interfaced. So the address lines are named as A0 to A15, where A0 represents the least significant address bit, A15 represents the most significant address bit. And it also has a data bus of 8-bit D0 to D7. Again, D0 represents the LSB or the least significant bit of data, and D7 represents the most significant bit of data. So this data line and address line, lower part of the address line, which is A0 to A7, are multiplexed with each other. So A0 to A7, the lower part of the address and the data lines D0 to D7 are multiplexed. So we use a common lines for both data as well as address. So it is termed as AD0 to AD7. So in order to differentiate whether these pins contain an address or data, it makes use of a pin called as ALE, address latch enable. So if address latch enable pin is 1, then the content on this AD0 to AD7 will be treated as address. If ALE is 0, then the content on AD0 to AD7 will be treated as data. So we reduce the number of lines or the number of pins on a microprocessor by multiplexing this lower part of address with the data content. So, and the 8085 microprocessor supports 8-bit IO address, input or output device address. So each IO device is connected to a microprocessor is assigned with an address. So a microprocessor can support 8-bit IO address, which means 2 power 8, 256 IO devices can be connected with your 8085 microprocessor. And another important aspect of a microprocessor is it contains registers. So putting a data onto the register and accessing the data by the CPU will be faster when compared to your RAM memory or external memory. So the important content is how many registers are available in a microprocessor. So here in 8085 we have about 6 8-bit general purpose registers. So it is named as B register, C register, D, E, H and N. So we can use these registers as a individual 8-bit registers, or we can also combine these registers together to make it as a 16-bit register. So in case of a 16-bit register, we have 3 combinations: BC register pair, DE register pair and HL register pair. So either I can use it as a 8-bit register or we can use it as a register pair, 16-bit registers. And the microprocessor also contains a 16-bit program counter. So program counter is a register which holds the address of next instruction which will be executed by the CPU. So it points to the next instruction which needs to be executed by the CPU. So here it is a 16-bit program counter because our address space is of 16 bits. Right? So our address space of memory is 16 bits. That is why the program counter is also designed to be in 16 bits. And we also have a stack pointer which points to the top of your stack memory. So top location of the stack is pointed and the address is stored in the stack pointer. It is also a 16 because stack is also a part of a memory and the address of that stack needs to be stored in this stack pointer. So it points to the top of your stack memory. And the stack will be growing downwards, meaning as I start pushing the data onto the stack memory, the address will get decremented. As I start popping out the data, as I start taking the data out of the RAM, out of the stack memory, the address will be incrementing. So the stack is growing downwards. And 8085 microprocessor, it supports 5 external interrupts. So external interrupts are required for interfacing an IO device. So whenever a peripheral wants to use the CPU, it will make a request. Upon request, the CPU will execute a program related to that IO device. So that is called as an interrupt. So here 8085, it supports 5 external interrupts. So they are trap, RST 7.5, RST 6.5, RST 5.5 and INTR. Where this trap is a non-maskable interrupt. So it cannot be stopped. So as soon as if I connect a peripheral device to this trap pin, if the peripheral device wants to use the CPU, then it will generate that trap signal. So it cannot be stopped. So it has to be immediately serviced. So the peripheral needs to be serviced immediately. Whereas other things, RST 7.5, 6.5, 5.5 and INTR can be masked, can be stopped. And 8085, it also supports 8 software interrupts. It also supports a serial data transfer. So a bit of data can be sent out from a microprocessor as well as it can get a bit of data into the microprocessor. So a serial data transfer is possible through SOD line. So SOD means serial output data. So one bit can be sent through this SOD line. Serial input data line is used for getting one bit into the microprocessor. It also has the ability to share its buses with the external bus controller. So if a peripheral wants to use a data from a memory, in that case, the peripheral will make a request to the CPU, then the CPU will try to take the data from the memory and it will provide it to the peripheral device. So here the requirement of a CPU is needed to do this data transfer operation. So by doing this data transfer operation, the CPU will not be able to do its own process. So in order to avoid that, a 8085 microprocessor, it also supports a DMA controller, direct memory access controller. So without making use of a CPU, this DMA controller can make the peripheral device to get the data from the memory. So the peripheral device can access the memory directly without the intervention of the CPU. So in order to do that, the CPU has to share its buses to the DMA controller. Then only the DMA controller can provide the data required for the peripheral device. So a 8085 microprocessor, it has the ability to share its buses with external bus controller. And 8085 microprocessor, it has 74 basic instructions with 246 opcodes, and it also supports 5 addressing modes. So addressing modes in the sense how the data will be accessed by the CPU during instruction execution. So there are 5 modes. Immediate addressing mode, meaning the data for an instruction execution is available in the instruction itself. So the data is provided in the instruction itself. Whereas in case of a register addressing mode, now the instruction contains a register and the register has the data for instruction execution. Direct addressing mode, instruction contains an address pointing to a data. Indirect addressing mode, instruction contains a register and the register has an address pointing to a data. And the last type of addressing mode is implied addressing mode, meaning the instruction has an assigned meaning. Right? So these are the 5 different addressing modes supported by your 8085 microprocessor. So immediate addressing mode in the sense the data is provided in the instruction itself. Register addressing mode, the instruction contains a register and it holds the data. Direct addressing mode, instruction contains the address and it is pointing to a data. Indirect addressing mode, the instruction contains a register and the register has the address pointing to a data. Implied addressing mode means it is understood by default. Now let us discuss the pinout of 8085 microprocessor. So this is a 40-pin dual inline package made up of ceramic material. You can see 20 pins on one side, another 20 pins on other side. So let us start with pin number 1 and 2. 1 and 2 is indicated by X1, X2. So X1, X2 is a oscillator connecting pin. So we can connect a crystal oscillator to this pin. So it can be connected with the oscillator of 6.144 megahertz. And remember, in 8085, it has a frequency divider circuit inside the microprocessor. So this 6.144 megahertz will be internally divided by 2. It becomes 3.072 megahertz. And that is the operating frequency of your 8085 microprocessor. Then we have this AD0 to AD7. So here you can see from pin number 12 to pin number 19 is AD0 to AD7. So this represents a multiplexed version of address and data lines. So the lower order address A0 to A7 is multiplexed with D0 to D7. So we use a common line or common pins for providing both address as well as data. Then how to differentiate it? Whether we have an address or data on these pins. That is provided by the ALE pin. So ALE will be used for determining whether I have an address on this line or I have data on this line. So then we have this reset out. So the reset out signal will indicate that microprocessor is reset. It is also used to reset other devices. So it gives an indication that the microprocessor is reset. So the devices which is connected to the microprocessor can also be said to be in reset mode. Then we also have a pin for reset of a microprocessor, that is reset in bar. So where this bar indicates it's an active low signal. So whenever reset is applied to the microprocessor, its program counter is set to 0. And also the interrupt enable flip-flop content is reset, and also HLDA flip-flops get reset. Then we have this serial output data and serial input data for data transfer from microprocessor to peripheral devices. So serial input data, for example, if we execute a RIM instruction, read interrupt mask instruction, then the data available on this pin, SID pin, can be obtained and it can be moved on to the 7th bit of your accumulator. So the data can be obtained from this SID pin and it can be loaded onto a 7th bit or MSB bit of your accumulator by using a RIM instruction. So this is serial input data. We get the input into the microprocessor. We can also send the data out from your microprocessor. So that is done with the help of a SOD pin, serial output data. So the data in the MSB bit of your accumulator can be sent out through this SOD pin by executing a SIM instruction. SIM instruction in the sense set interrupt mask instruction. So the important thing here is, even though I put a data onto this MSB bit, so this data can be sent out through this SOD pin only when I have SOE to be 1. This is serial output enable. The serial output enable is 6th bit of your accumulator content. So 6th bit of your accumulator content, if it is set to 1, then only the data available on the 7th bit or the MSB bit will get transferred through this SOD pin. So this bit can be used for interfacing an LED so that I can make a toggling of an LED depending upon what type of logic we try to put it onto the data here. We have 5 interrupt signals like trap, RST 7.5, 6.5, 5.5 and INTR. And there is an acknowledgement signal for the INTR interrupt request. There is also a ready signal. So ready signal is used by the slow peripheral devices which is connected to the CPU. So whenever we connect some slow peripherals onto the CPU, it needs to provide some information to the CPU, because in order to have a proper transaction, the peripheral device should be ready to accept the data. So it should provide a ready signal so that the CPU will understand, okay, the peripheral is ready to accept the information, so the CPU can transfer the next information to the peripheral device. So that is taken care by your ready signal. So it uses for synchronizing the fast CPU with the slow memory or peripheral devices. And there is another pin named as IO or memory bar. So which indicates whether we are performing an IO operation or a memory operation, to differentiate whether the CPU is performing an IO operation or a memory operation. So active high in this pin indicates it is doing IO operation. Active low on this pin indicates the CPU is performing a memory operation. We also have a read bar and a write bar. Both are active low signals. Whether the data is read from a IO or memory device, or whether the data is written onto the IO or memory device. So that will be performed using this RD bar and WR bar. So together with the IOM bar, RD bar and WR bar, we can specify the operation by the microprocessor. So for example, if RD bar is 0, WR bar is 1 and IOM bar is 1, which means 1 means it's a IO operation, and we are going to perform a read from a IO operation. So 8085 reads information from the input port. Same way 101 indicates again an IO operation, and the CPU is going to do write on the IO port. So 8085 writes information to the output port. So in case of IOM bar to be 0, it indicates it's a memory operation, whether we are doing memory read or memory write. That is specified. Then we also have hold and HLDA pins. So hold indicates if I have a DMA controller, it wants to use the buses of your microprocessor. Address bus, data bus, RD bar, WR bar and IO lines. The DMA controller wants to use it. So it will make a request for it. So the request comes through this hold line to the CPU. Upon receiving the request on the hold line, the CPU can respond to that DMA controller through HLDA line, hold acknowledgement line, which means the CPU is ready to transfer the address, data, RD bar, WR bar and IO M bar lines to the DMA controller. Thereby the DMA controller can use those buses for performing the transaction between an IO device and the memory without the intervention of your CPU. It can be used for doing the transaction between the peripheral and the IO device and the memory without intervening with the operation of your CPU. Then we have status lines S0 and S1. These signals indicate what type of operation is being performed currently by the CPU. So it needs to be taken into account with the IO M bar signal. So as I said, IO M bar signal, it is 1 in the sense it indicates IO operation. IO M bar signal, if it is 0, it indicates a memory operation. So if IO M bar signal is 0, it represents a memory operation. Depending upon the status lines S0 and S1, we can understand if it is 00, then the CPU is in halt state. If it is 01, then memory write operation is being performed. If it is 10, memory read operation is being performed. If it is 11, then opcode fetch is being performed. Same way, if IO M bar equal to 1, which means it's a IO operation. In IO operation condition, if S0, S1 is 01, it's a IO write operation. 10 means IO read operation. 11 means it's an interrupt acknowledgement signal. Then we also have a clock out signal. Pin number 37 is your clock out signal. So a microprocessor can be used to generate a clock signal, and this clock signal can drive other peripheral devices connected to the CPU. So it can be used as a system clock for devices connected with the microprocessor. Then we have power supply lines. VCC is in 40 pin and VSS in pin number 20. So VCC will be plus 5 volt and VSS will be a ground line. So these are the different functionalities of each and every pin of your 8085 microprocessor. So in this tutorial, we have discussed about the features and pin out details of 8085 microprocessor. Thanks for watching. Please subscribe for more technical learning. Thank you.